Hello, welcome back. We're going to look at relative positioning today. So we've built a few different components of our model, and now it's time to build out the relative positioning encoding scheme. So we'll jump right into it. If we look at the paper, essentially they don't tell us much. They say we're going to use the T5 relative position bias. And so you have to go into the T5 paper, and for both of these papers, I've pulled out really all of the information about this scheme. And I'll summarize for you. We want to create a relative position embedding matrix that looks something like this. So pretend on this first row that we're dealing with the first token. Relative to this first token, the first token itself is 0 tokens away. And the one to the right of it is 1 token away, 2 tokens, so on. If we get down here, in this row, we'll be dealing with this token. And relative to it, this one is 1 behind, 2 behind, 3 behind. So essentially, we want to build out this relative position matrix. And then we're going to assign an embedding to each of these positions. And that is what relative positional encoding is. And if you remember, or if you've seen absolute position encoding, you might just do something like this, where it doesn't matter what word you're dealing with. If you're dealing with the 5th word, the token embedding will be number 5, or number 6, or number 7. So that's absolute. We just care where it is inside of the sequence. With relative, if we're dealing with the 6th token, we don't care that it's the 6th token in the sequence. We just want to know what's immediately to its left, what's immediately to its right, and so on. So that is relative position encoding. The modification with T5 is that they say, well, say you have a 512 length sequence. As you go really far out, relative position does not appear to matter at long range. And T5 relative bias puts all long range tokens in the same bucket. So one modification we're going to make is that once we get to a maximum range, we're just going to put everything in the same bucket. So in this, say we only wanted 5 buckets, the 5th bucket would just contain everything that is beyond those bounds. Next, the other modification for T5 is that, say we're here, we're interested in 6 buckets to the left and 7 indices to the right. Rather, indices to the left, indices to the right. These are different tokens. So what we're actually going to do is, for up to n tokens away, we're going to use the exact index. So if we're using max exact, we want to have at maximum 3 indices that will be the exact index. We'll do that. And after that, we'll start to actually scale the values logarithmically until we reach the maximum number of buckets that we want. So we'll see an example of this as we build it out, but the intuition is something like here, say, maybe the first 3 indices are exact, so it looks just like this. And then instead of 4 and 5, it's 4 and 4, and then it's 5, 5, 5, 6, 6, 6, 6, 6, 6, and so it logarithmically scales. So that is really the essence of T5 positional embedding. And so we're going to build that out now. So just to solidify what I've said here, we have our main idea, and then we've got a recipe. And this is just a good exercise if you want to keep notes and a to-do list of what we have to build. So here we have our recipe. Construct a relative position matrix. For offsets larger than what we want, start to spread offset values into a finite amount of buckets. We'll map everything onto one value, initialize embedding weights, and we'll assign these index values to the embedding weights, and that will get added into our attention. We can make a note here that start to spread offset values logarithmically. Okay, so now we have a recipe. I'm going to import a few functions, or rather a few libraries. And this is just so we have torch, numpy, math. And now we'll initialize some of our beginning variables, just so we can build this and see what's going on. So while in the actual model, we'll use long sequences, here we're just going to use sequences of 14. And I've just picked this because when we start to look at the outputs, we can actually see everything that's going on. So we'll build a toy example, make sure it does everything we expect, and then we'll put this into a Python class such that we can put in any sequence and max context length, any number of buckets, any distance. So here we're just doing 20, and it doesn't matter much. But eventually we'll want to put this to 128 as the paper specifies. Okay, so this is the number of buckets that we will spread our position indices into. Max distance doesn't matter right now. The sequence length, we're just going to say that we have sequences of 14 length. And max context length, this is, if you imagine our attention matrix is built using query and key. And so we're constructing out of n query tokens and m key tokens. So probably to your intuition, this is a square matrix. I'm only adding this in as a different variable because when it comes time to put in XL transformers, or rather to implement that, we'll need to put in recurrence. And so this is going to be equal to sequence length, or when we start putting in XL recurrence, we're going to concatenate that onto the keys. So our matrix won't be square, both for the attention and because this is just going to be added straight onto the attention. We want it to be the same shape. That's just a caveat, but really we're going to treat this as a square matrix. And this is how it works whenever you do not concatenate further recurrence. Okay, first step is construct one of these, a relative position matrix. So here I have our query tokens, or rather, I'm just going to show the range of our query and key tokens. And if we look at these, great. So we have 14 as the range of our sequence. And now we need to construct this matrix. So there are a bunch of different ways to do it, but what we will do is we will create one row and one column, and we'll subtract these, and this will actually give us our relative attention matrix, which is kind of a nice trick for doing this. So we're going to reshape this one into a column vector. And let's look at that. Okay. And now creating a relative position matrix is really just as simple as there we go. So that was a really simple way to do it, and this is a nice trick. There are a lot of other ways, and you might scratch your head trying to figure out how to do this with built-in PyTorch functions. But this, to me, looks like the simplest way. So let's remember that we're building a decoder model. So we'll actually never see into the future. We're never going to look at these indices. So let's say this is one sentence that's 14 tokens long, and we've split it into 14 examples. We're never ever in the first one going to see ahead of the current word we're at. So we need to mask these out, this upper triangle here, and we need to make this bottom triangle positive. We don't need to map to negative weights. It's just for convenience. We'll just call this embedding 1, embedding 2, instead of only having negative indices for embedding. So we'll just call, first we'll negate this. Oops. So we've just swapped the sign of everything in this matrix, and now we just need to mask out the top right corner. And so we can just say, we'll cover this matrix and take the maximum of whatever is in at each index, or 0. And so all of these negative values will get turned to 0. So zeros like just creates a matrix of zeros in the same shape as a predefined matrix here. Great, so now we have our decoder ready relative position matrix. And now we need to add the T5 modifications. I'll add this in. If we remember, we have 6 buckets, and I've just chosen this because it's easy for us to see. So remember that we have 6 buckets. The first 3 buckets are going to be exact indices, and the last 3 buckets will act as true buckets where we start piling in a bunch of indices and we spread them over these last few. So we're going to have 3 max indices. And now we want 2 masks applied over this relative position matrix. And this is our way of approaching this. So remember our two modifications. One is to make sure that for the first three indices, the index is preserved. And then for the indices beyond that, we want to logarithmically scale them up to a max sequence. And we want to logarithmically scale this into the remaining 3 buckets. So one of our masks is going to just be a Boolean that we can apply. And this is going to be called is small, and this is just telling us whether or not the value is below 3. And so wherever this is false, wherever it exceeds 3, we're going to apply another mask that we'll build now. Let me get this out of the way. Another mask that will logarithmically scale the remaining buckets. And I've just written something here so that we can remember what's going on. Okay, so I found this function in the Hugging Face library, and it's in the T5 library, and it's a little strange, but we already have an intuitive idea of what it's doing, so I'm not going to go through the details. I'll copy it here, and sort of, you can see a small breakdown. I'm not sure why it looks exactly this way. I think there are different ways of logarithmically scaling these in the desired way, but this is what the authors did, so we're just going to go with this. But remember, our entire idea is to map it logarithmically out. So indeed, if you have some other kind of idea about how to scale these values out, then you would just drop that in here. And you could change the max exact. So this is their positional encoding scheme, and I'm sure you can come up with a lot of different relative positional encoding ways to distribute your position embedding indices across a very long sequence. So this is what we've got. And let's see if we can get, and I've just copied the function there without converting it to int, just so we can see a little bit what's going on under the hood, and you can verify that this is happening correctly. So these are floats, and these are very small. These are going to be 0. And then everything else, we're going to turn that into an integer. And so you can start to see, say in this bottom example, that forget this, because that will be mapped exactly. Everything following that is logarithmically scaling outwards up to the maximum. Now let's just apply the integer transformation. And so negative infinity goes to the lowest integer that they have, but right, we look down here and it's 1, 2, 3 through 3, 5 4s, 3 5s, but that would keep continuing, so there's probably 8 or 9 5s. It's logarithmically scaled. So this is doing what we want. We're just verifying at each step that this does what we want, and this is a good way to build it. Okay, so now we have 2 masks, essentially, and we're going to apply these up here, and this will give us the relative position encoding scheme that we want. So where, torch where, is going to map what we want. So where works by saying, here's the condition, if true, else y. So these are our 3 variables. Okay, let's see what we get here. Now let's look at this and verify. Okay, so all of the zeros in the upper right triangle, great. As we look at one of these examples, the first 3 are always exact. There's no logarithmic scaling on the first 3. And after that, it does scale logarithmically. So this is doing exactly what we want. And we have this kind of small example so we can examine it and see that it's worked in the way that we thought it would. So we've built this matrix out, and now we're going to basically use these to index into a positional embedding matrix. And so whenever something needs the third index as to say, I am in the third position under this scheme, we're just going to index into an embedding matrix, pull out that embedding, and then we're going to add that embedding onto the attention map. So these will all be turned into positional embeddings that we initialize randomly and are trained with the model. And this will just get added on top of the attention scores. And the way they do it here is that there is one of these per each head. So let's say we have 4 heads. This will be the embedding layer, and then, right, we have 6 buckets and heads. An embedding layer is just, really, it's a linear layer that's good for sparse inputs and one-hots. So it does the same thing, but it's just a little more efficient. Let's see that. Okay, great. So we have 6 buckets, and these are 4-dimensional. So we could actually, let's look at the weights. Just weights. So we have 6 of these buckets, and we're spreading it out for now just across 4 heads to see how this works. And now we're just going to index into this with our matrix. So what we really want is our relative position values. And these take the embedding matrix, and this is the syntax for indexing into this, and this should give us what we want. Position bias. Okay, so we have 4 of these 14 by 14s, and inside of each one we've replaced these indices with the appropriate embedding weight. When we go to actually pass that through, we'll just be applying it per head, and so it's going to be a little nicer to change these dimensions around, but we can look at that as we start to build it into a positional embedding class, which is what we'll do now. Okay, so when it's time to feed this into the model, it's inconvenient to use this shape. So we're going to deal with it inside of our position embedding class, which I'll show you in a second, but just for kind of brevity, I'll show you what's going on here, where right now the dimensions are sequence, context, and heads. And to make this work with the rest of our model in a nice way, we're going to reshape it so that it's a batch dimension, which we'll just create as none, or a 1, and then heads, and then sequence and context. So the first thing we can do is we want to transpose these 2 dimensions. Great, so we've put the head in front. And then what we want to do is unsqueeze. And this adds a dimension. Rather. So this is what we want to end up with. We're transposing and then adding an empty batch dimension in front. Oops, okay. All right, there we go. So I've packaged this all into a class, and this is what we'll use as we're actually training our model, because we can very easily call it. Let me grab the class here, and there won't be anything new in here. This is just converting this into class. We do have a scaling factor here. I think this is the only new thing. And before we actually add this to our attention scores, we have the option of scaling it. But that's not so important, and we can test that as we're actually running the model. But otherwise, everything should look the same. It's just packaged up nicely. And there we have it. That is our relative position encoding scheme done.